Ben bugün çok mutlu oldum. Işık Üniversitesi'nde hiç bu kadar sürprizle karşılaşacağımı bilmiyordum. Işık Üniversiteli hocalarıma dönük olarak katılımcılara, elektrik, elektronik mühendisliği bölümünden olmayan hocalar için söylüyorum. Vallahi Yorgo bir mesaj atmış. Ben sürekli seyahat halinde olduğum için o detayı takip etmedim. Sonuçta bu bir RFIC Design Workshop. Yani elektronik fevkalade detayı, dünyayı çok ilgilendiren, herkesin cebindeki telefonları ilgilendiren bir konu. Dünyadaki insan sayısı kadar neredeyse cep telefonu var. Çok büyük bir pazar. Tabii pazarın gidişatı değişiyor. Ama e, yani psikoloji bölüm başkanımız, iktisat bölüm başkanımız, işte işletme bölüm hocalarımı görmek beni çok mutlu etti. Belki bunu bir avantaj olarak da kabul edebiliriz. Işık Üniversitesi'nde özellikle teknik aktiviteleri her konuda teknik aktivite, sosyal bilimler ve mühendislik ve fen bilimlerinde, temel bilimlerdeki aktivitelerimiz var. Çok çok güzel konferanslar yapılıyor burada, workshoplar yapılıyor. Hepsini izliyorum. Bütün fakültelerimizde, Güzel Sanatlar Fakültesi dahil olmak üzere çok güzel sergiler yapılıyor. Tabii bu seneki başarımız da oldukça iyi. Diğer vakıf üniversiteleriyle karşılaştığımız zaman. Ama relatifli yani. Çok çok daha iyi olmamız lazım. Önümüzdeki aylarda Türkiye'deki ekonomik durumun da bazı sıkıntıları olacağını öngörüyoruz doğrusu. Ne olur bilmiyorum. Tabii onu uluslararası ilişkilerdeki arkadaşlarımız değerlendirsinler ve bizleri bilgilendirsinler. Yani bölge ülkeleriyle olan sıkıntılarımız sıfır dış politika sorunu, sıfır sorun politikası komşularla. Aslında sıfır sorun politikası özünde ben uluslararası ilişkilerin usulundan anlamam. Ama yani Atatürk'ün işte bazıları söylüyor Kemalizm nedir, Atatürkçülük nedir? Millet bir şeyler söylüyor. Mümtaz Soysal bile falan temkim yaptı geçenlerde bir programda yapıyor oluyor. İşte yurtta sulh, cihanda sulh'den başka bir şey değil aslında. Milli misaki sınırları. Yurtta sulh, cihanda sulh demek herkesle sorunsuz bir uluslararası ilişki demek anlamına geliyor. Ama pratikte de öyle olmuyor. Gelinmesi istenen nihai nokta o. Şimdi işte sıkıntılar ortada. Her gün gazetelerde, televizyonlarda dinliyoruz. Arkadaşlarımız bizi yönlendirsinler. Ekonomideki arkadaşlarımız, finans bölümündeki arkadaşlar finans açısından nasıl tedbirler almamız gerektiğini düşünsünler. Elektrik elektronik mühendisliğinin bu arada öncülüğünü yapmış olduğu bu workshop'ta teknik olarak ülkemizde neler olabilir biraz onun üzerine duracak. Ben diyorum birkaç arkadaş daha gelecek. Ben formal olarak açılışı başlamadım ama en azından bu fırsatla bu düşüncelerimi paylaşmak istedim ve özellikle konu dışındaki olan hocalarımıza bu sabah bizde oldukları için, tatlı uykularını yarıda bıraktıkları için gerçekten çok çok teşekkür ediyorum. Şimdi yine kameralar için Türkçe bir şeyler söyleyeyim. Then I'm going to switch to English, Franco. Şimdi RF demek radio frequency demek. Yani bizim telsiz olarak konuştuğumuz frekanslara radyo frekans diyoruz. RF biraz daha cep telefonları içine giriyor. Yani bütün haberleşme dalgaları radyo frekanslar, radyoların kullandığı dalgalar işte RF kısaca radyo frekans dalgalar. RFIC entegre devre, tümleşik devre. Duran hocamız onun adını vermişti. Şimdi dünyada bu çok önemli bir noktaya geldi. Türkiye'de de çok önemli bir potansiyel var. Bizi bugün burada, bu hafta, bu workshop'ta özellikle beni de fevkalade heyecanlandıran ilginç gelişme şu. İstanbul Teknik Üniversitesi'nde yıllar önce işte Duran hocamızın başlatmış olduğu altyapı, aradan tabii köprülerin altına çok sular aktı. İki tane genç arkadaşımız, Devrim Akşin ve Türker Kuyel isimli iki kafadar. Bunlar Teksas'tan Teknik Üniversiteye geldiler. Eski Teknik Üniversitede benim de çok sevdiğim iki genç arkadaşım diyeceğim. Jasmine'i de getirdi. Jasmine, you understand my Turkish, right? A little bit. Ve teknik üniversitede yeni bir modern altyapı geliştirdiler. Ben bu arkadaşlara İstanbul Üniversiteli olarak destek olmayı bir görev adettim. Ve çok da güzel paslaştık bu Aref IC tasarım grubuyla. Onlar bizim öğrencilerimizin çalışmalarında, doktora tezlerinde, master tezlerinde yer aldılar. Ben de İstanbul Üniversitesi'nden arkadaşlarımın aşağı yukarı bütün doktora tez jürilerinde keyifle görev aldım. Hatta son birkaç senedir de Japonya'dan döndüğümden beri İstanbul Teknik Üniversitesi'nde Advanced Telecommunication diye bir ders veriyorum. Doktora düzeyinde herhalde doktora sınıfları içerisindeki en kalabalık kurslardan bir tanesi. En kalabalığı desem daha doğru olacak. Sebebi şu, İngilizce fazla ders yok. Sevgili devrime bir gün dedim ki Türker'le beraber, ya çocuklar bakın biz Aref'te radyo frekans, mikrodalga mühendisliğinde, burada bu işlerden anlayan işte Ahmet var, Ahmet Aksen. IC yapmak zorundayız ama elektromanyetik dalgasız IC olmuyor. Bir tane kitap çıkarttık. Derste de o vallahi günah bile geldi. Senin öğrencilerin hoca ondan önce gelemez diyorlardı Günancığım. Günhan Dündar, Boğaziçi Üniversitesi eski elektronik mühendisliği bölüm başkanı. Çok değerli bir arkadaş. Sonuçta şöyle bakın, bizi bir araya getiren İstanbul Teknik Üniversitesi, Boğaziçi Üniversitesi ve beni bir araya getiren olay nedir biliyor musunuz? Uluslararası konferanslardaki beraberliğimiz, birbirimizin yapmış olduğu çalışmaları bilmemiz ve o güzel çalışmalara duyulan saygı. Sonuçta biz böyle bir grup oluşturduk. Sadece Türkiye'de değil, bu grup Franco Maliberti'yi ben ilk defa, Franco burada, he is a very good colleague of mine. Çok iyi bir arkadaş, çok iyi bir dost. Gerçekten muhteşem bir insan. Buradaki arkadaşlarımızın da doktora, işte devrimin doktora hocası Texas A&M'de. Franco da dünyanın her tarafını karış karış geziyor. Texas A&M Üniversitesi'nde de uzun bir süre profesörlük yaptı ve birçok Türk doktor öğrencisiyle çalıştı. Bu tabii çok önemli bir ayrıcalık ve Türkiye'yi, Türkleri, hatta Kuzey Afrika'da, Cezayir'de falan da çalışmış ve burada Pina var. Pina tabii, she is the driving motivation behind Franco. No question about that. Şimdi bu tarihçeyi ben sizlerle paylaşmak istedim. Yani uluslararası konferanslar, IEEE'nin en ileri düzeydeki konferanslarında biz İstanbul Üniversitesi, İstanbul Teknik Üniversitesi, beni Işık Üniversiteli olarak da, o zamanlar gerçi Işık Üniversitesi'nden ayrılmıştım. Gerçi o dönemlerde de epey güzel şeyler yaptık benim rektörlüğüm sırasında burada. Boğaziçi Üniversitesi ile Günhan'ın mesela ikizleri var. Çok şeker bir eşi var. Muhteşem çocuklar. Kocaman oldu Günhan. Nereye saklandı Günhan'cığım? Harika. Şimdi bu konular çok önemli. Şimdi önemi nereden kaynaklanıyor onu da söyleyeyim. Biz Türkiye'de bu grup birbirimizi görür hale geldik, katılır hale geldik. Konferanslarda birbirimizin derslerine davet edilir hale geldik. Sonra düşündük ki burada çok güzel olan bir şey şu. İki Türk bir araya geldiği zaman bir diğerinin paçasından aşağı çeker. Halbuki bu bizim bu güzel nezih grupta böyle bir şey söz konusu yok. Karşılıksız, beklentisiz dayanışma anlayışı var. Ve bu dayanışma anlayışını ilk defa geçtiğimiz dönem kanunlara da bypass ederek diyeceğim artık buna, 4 üniversitede bir ortak kurs yaptık. Bunun güzel sebebi de Franco'nun, ya Sıddık ben Türkiye'ye acaba sabbatical'a gelsem mi? Ondan önce de bunları biz konuşurken olacak olmayacak, ya gel dedim Franco, tamam biz nasıl bir şey hallederiz. Fakat Pina bu işten emin değil. En son Endonezya'da, Endonezya'nın o meşhur adası var. Bir Japon konferansında tekrar bir araya geldik. İkimiz de invited speaker olarak katıldık. Ve Pina'yı ikna ettik. Dedim ki Pina bak, bizim Işık Üniversitesi çok güzel. Teknik Üniversite çok güzel. İstanbul çok güzel. Zaten İstanbul'u seviyorlar. Pina'yı biz Endonezya'da, Bali'de ikna ettik. Yoksa Franco buraya gelmez. You understand a little bit what I say? Well, yeah, Franco, you understand Franco. Well, I'm going to switch to English. I'm just giving you the history a little bit. For the TV cameras, I just wanted to make a few words in Turkish. Please apologize my situation. The history is this. We were several selected guys in Turkey from Istanbul University, Technical University of Istanbul, Boğaziçi University, and I have several hats. I am part of Istanbul University. I am chairing the electronics department. I am also chairing the Işık University board of trustees. So and Boğaziçi University. I met all these beautiful guys as well as Franco in IEEE Circuit and System conferences and other related conferences. Sometimes Japan, sometimes in Malaysia, sometimes in Indonesia, Bali, or whatever, and Canada. So eventually, we got together here in Istanbul. This was really very special. Then Franco said, can I come to Istanbul on my sabbatical? I said, well, why not? But Pina wasn't sure whether she was going to release Franco here or not. All of a sudden, he was involved with a terrible event in Mexico. I said, don't go to Mexico, Franco. Istanbul is better and safer. So I was right, I guess. This was in Bali. So anyway, so eventually we convinced Pina in Bali, Indonesia, last October, I guess, right? Then we decided to set up a course in Istanbul. We said Technical University Istanbul, well, as a location, either Işık University Maslak campus or ITU was going to be the location to meet. So thanks to Yorgo and Günhan and Dündar and Işık University and Istanbul University, we somewhat managed to get together. And Franco spent his last term here on an off basis every other week, came to Istanbul after he recovered from the accident happened in Mexico. So this is how we decided here. So the motivation behind this organization is absolutely Franco Maliberti and Devrim Akşin. I'd like to express my special gratitude to Franco for being an outstanding friend and an outstanding instructor, advisor, and with a good will. Then we had Günhan. I talked to Günhan. I said, look, Günhan, we are organizing a joint course in Istanbul. He was so kind to open up his intellectual property, I would say, so that we can put together all these RFIC guys. RFICs are quite important because every cellular handheld does have thousands of chips in it, or millions of transistors in it. So it's quite important, and I believe in Istanbul, especially in Istanbul, we have quite a lot expertise in designing ICs, Technical University of Istanbul, Boğaziçi University, and I believe as an electronics engineer, I believe that an electronics department cannot be standalone, cannot stand on his feet without having an IC design course. At Istanbul University, I was pushing all my staff, my students, to open up this store, and I had no background in IC design. So I was sometimes going to Erşet Akçosu, who's a very good friend of mine, and Kemal is here, Kemal Ozansoy, Kemal is here, and we spend days and nights, and even we have done some designs all together and presented in Japanese workshop in Istanbul, held in Istanbul, together with Erşet and his team. But I couldn't convince them to come to lecture at Istanbul University. So anyways, and I was also pushing Ahmet Aksen, the chairman of Electronics Engineering Department of Işık University. And I know he doesn't have that background, but we had to somewhat to produce this motivation here to start IC design. You cannot have the foundry. Foundry is quite difficult. There is the production facility. But no university has, except a few maybe, has foundry, but design is quite important. You can just purchase a software, rather license it like Cadence or Mentor. Boğaziçi has Mentor. I'm sure they're going to switch to Cadence soon because everybody is working with Cadence. And at Istanbul University, I licensed Cadence, and even we help Technical University of Istanbul to renew their Cadence license some time ago. So we started to work together. So the motivation here, then eventually, myself, Devrim and Günhan, we said Istanbul could be this education center for RC design. So you don't need much. I mean, all you need is continuous education programs like this, a workshop. And we need good students. At Istanbul University, I know that there is a solid number of students working together with these groups. So then we said, okay, let's push it. And Franco was highly motivated about this issue, and he encouraged us. Then we set up, then he said, can we set up a center of excellence among the universities and industry? And thanks God that Aselsan recently purchased Microelectronics Corporation, which is located in the Techno Park of Istanbul Technical University. So we got the sponsorship, and Aselsan sponsorship, and organized this workshop. So the first attempt was, as I mentioned before, it was the course initiated by Franco Maliberti. I hope we can continue this course next year too, depending on the availability of Franco, depending on our situation. I hope we can do it. And then we initiated the idea of having continuous education workshops in Istanbul. And Aslı Divish is not here, but she was so kind to carry out the secretariat of this workshop. So eventually we put all these 4 universities together. I'm sure we can easily have Middle East Technical University in Ankara to join us. But we said we want to make this location in Istanbul. In Ankara there is a very important nanotechnology center under Tayfun Akın, and I was with his team last week. We chaired the Mediterranean Microwave Symposium 2012 last week in Istanbul. So we put together all these nano guys too. Well, again, we generated the idea to organize a short course on RF radio frequency RFIC design. Well, immediately Franco, Devrim, Türker, and Günhan and the team, the technical committee got together and set up the outstanding workshop. It's being held now, starting today at Işık University. So I'd like to express my special gratitude to all who organized this workshop. And special thanks goes to Aslı Divriş. She's not here today, and Kerem Ok. Kamil is here. So they have done a great job preparing the web page. I attended several meetings. I initiated the meetings at the beginning of the stuff, but somehow we made it. And Barbaros Şekerkıran, I think he's on the way. They are trying to find this classroom here of microelectronics, and he was keen to push the industry. So this course is fully sponsored by industry and Işık University and technical support of Istanbul University, Istanbul Technical University, and Bosphorus University, Boğaziçi University. Well, eventually I should really say that, and I shouldn't forget Jasmine too, because she's the hidden power behind Devrim, and Pina, she's very special for me. We have been together for years in various conferences as well as in Istanbul. So finally she made to come to Işık University. This is great. Well, of course, thanks goes to all our instructors. Francesco from Pavia University is going to be talking about the basics of CMOS receiver front ends. It is very important for me because we are designing a lot of front ends and back ends for various companies in the world. And I'd like to also express my thanks to Bello, ST Microelectronics. I think this is the French division, right, Franco? Didier is from the French. It's on the border, French and Italy. They're nearby, now close enough to Pavia University. Pavia is a very old city, 1,000 years old city, really, with everything. I mean, with the buildings and everything. It was wonderful. And Mohammed Ismail, Professor Kustar, is going to come from all the way from Saudi, right? You see the one. And I'd like to thank to Michel Perrot, Master Institute, and Patrick Reinhardt from Catholic University Leuven in Belgium, and Franco, he was kind enough. Actually, Franco is the godfather of analog digital converters, the ACs, in the world. He's been doing great since last decade. I mean, he's been working hard. Actually, his background is not electronics, rather physics. But that really helps him out a lot because if you don't understand physics and the propagation of waves, and you won't be able to spin high-speed circuits. So this is great. So I'm gonna make the long story short. I'm really honored to be here. I'd like to thank to all the social scientists. I can't believe this. This is Yorga. But what I'm gonna say at the end, and I'm gonna repeat this in Turkish, so that it is going to be understood by everybody and the cameras too. Maybe this is going to be news on TVs, on the Turkish media, soon on the social media as well. Well, what we have done here is something very important. What is important? Pavia University, Işık University, Technical University of Istanbul, Boğaziçi University, Istanbul University, and the other guys, and all the instructors coming from the other universities, we set up a course. This is a very high motivation. It's the result of a high motivation. It is our motivation to make Istanbul as the center of continuous education in high business, high technology. So RFIC design extremely high technology. It is special. It is one of a kind. And so what we say is, we don't say that we're going to be setting up the best university in Istanbul. Oh, we can do this, but not tomorrow, not the day after tomorrow. It's going to take years. But we can collect all the outstanding, top-notch people all around the world. Hocam hoş geldiniz. Barbaros hoş geldin. I'm going to give a short introduction for Professor Leblebicioğlu, who was my electronics professor at Technical University of Istanbul. Well, this is very important, but we can bring here the best people. So we have the best people here in the world, in this course. So we can invite the best students of the world to unite, to come to Istanbul in all the areas. So this is easy. If we can do this continuously, I think we can gain something here. And eventually, if we can put the national power together regarding in the selected areas, then we can really initiate a center of excellence in IC design. Bit and pieces, we have some centers in Ankara, in Istanbul. Well, in Istanbul, Technical University of Istanbul is the leader. In Ankara, Middle East Technical University, somewhat, maybe a little bit, Bilkent University, they did also start some nanostructures. And the other universities can join, and the willing students who really want to participate in this business will be great. What is important here, we don't really think from the national point of view. No way. This is not a nationalistic approach. We should be able to get together from all around the world to put a force to produce new ideas, to produce new chips, new technologies based in Istanbul. Why in Istanbul? Well, the reason for that, we started from Istanbul just because of Professor Duran Devletbicioğlu. Duran Bey, he's a great professor. He was the great motivator, and he initiated the modern electronics at Technical University. I was the first student, I guess. You start teaching IC design, the chips production. At that time, I'm talking about the late 60s and early 70s, not 74. 69, 70, 71, 72, 73. I left Technical University at 73. At that time, IC design did not exist. There was only one book, partially translated by Professor Santur, Yıldız Leblebici, is the wife of Duran Devletbicioğlu. She was also my professor, my instructor in electronics. So they started thick film laboratory at Technical University of Istanbul. It was the first of its kind. So we were able to catch up with the whole world, really. This is great. The reason that we are here this morning, just because of this initiative taken by Professor Leblebici, I'm delighted to have him here. I'm really honored to be his student, and thanks to him, on behalf of Turkish government, all the Turkish students, that he initiated this effort. And eventually, one of his students again, Erşet Akçasu, Dr. Erşet Akçasu, he's a very important name, leading name. He started a company. He's got several companies in the US. He started a company in Florida. It's called Erşet Akçasu Yazılım Software. This is very important. They do IC designs, many kind of IC designs, not Turkey, for Turkey. They do some work for some local companies here, but basically they work for the whole world. And there is another company initiated again by Akçasu. The name of the company is Microelectronics, and the general manager of the company is Barbaros Şekerkıran. He's another follower of Duran Devlevici. Thanks Barbaros that he really made microelectronics, and the company was bought out. The major shares of the company was bought out by Aselsan, Military Industries of Turkey. This is another positive development, I will say, because Aselsan is the leading company, really needs that infrastructure. They're doing excellent designs over there. So there are several, I counted about 17 companies from all around the world, located in Istanbul, nearby Istanbul, Gebze and so on, including Hittite Corporation. You say Hittite, it is Hittite. It was established by Yalçın Ayaslı. He was an Ortadoğu Middle East Technical University guy, and they got his PhD from MIT, and for years he worked for Raytheon and so on. So we have that company too. There are some other little companies. That is to say, Istanbul has a potential to become a design center, let's be modest, at least in the region, in the Middle East region, maybe for Russia and the other neighboring countries here, and maybe for Greece as well. So in Balkanian countries, in the region, and we can we can do a lot for the Turkic company, the Turkic region, for Asia, and Far East is working hard on that, of course. So let's give it an attempt. Again, thank you so much to the whole audience, all the students participating in this course, and I hope you enjoy it and have a pleasant stay on Işık University Şila campus as well as in Istanbul. Okay, thank you very much for your patience. So I'd like to ask Franco to say a few words maybe for our audience.
Yeah, after this very long description of Professor Yamant, I think there is not much to say. He mentioned everything, and he has an excellent vision. So I am sure that this vision will become a reality because he has the energy, and this country, Turkey, is full of very enthusiastic people. It's full of young people that is different from my country. We are a bit old, How is an old country? Not only me. But, I hope that I can contribute to this dream. I hope that with the help of a young generation, you will be able to have success in this microelectronic area. I had some experience, I can help. I hope that, as Professor Yamat mentioned before, my wife will be happy here. And let's see if, this initial activity will produce new things, will produce new events, and also will start generating knowledge in this area. The kind of knowledge that is necessary to generate companies and high level job. So thank you to everybody. Thank you to my former student Devrim, who is putting a lot of energy in this activity, to Turker, and to the friend, and to very good friend and expert, Gunam, from Boğaziçi University. We together, we can have a good contribution to this idea. Thank you very much to everybody.
Good morning. I'm under the pressure of what Siddiq said about myself. I thank him. I also thank him for the organization of this workshop, and also to Professor Meloberti, who contributed a lot for the organization of this workshop. I think this is the first one in this area organized in Turkey, getting together the designers of ICs or people related to the design of IC. I hope this will be a good first step for such organizations. I'm happy to see that a lot of young people attending this workshop, and again I hope it will be the first step, and during coming years we'll have many similar and fruitful organizations like that. Thank you for your coming here, and hope a successful meeting. Thank you.
I just want to thank each and every one of you to come to Işık University to this workshop. We are very enthusiastic to host such a esteemed audience as well as esteemed teachers, lecturers. We believe that this event is really important. It is because although we have a modest contribution or a modest number of electronic industry people here, but hopefully in the coming years the mixture of academia and the industry will be equal, and it will contribute to exchange of idea, more close relation between academia and the electronic industry as it's supposed to be. Now, Dr. Yarman and all the other speakers give enough information and explain the motivation behind all this organization. So I would like you to just move to the classroom so that we can start with our first lecture with Dr. Svelto. Okay?
Maybe.
So,
The other one.
your I would like to introduce Dr. Svelto. He received the laureate and PhD degrees in electrical engineering from the University of Pavia, Italy, in 91 and 95 respectively. During 1995 and 1997, he taught at the Industry Grant for Research IRCMOS. In 1997, he was appointed assistant professor at the University of Bergamo, and in 2000, he joined the University of Pavia, where he is now full professor. His current research interests are in the field of RF and high-speed integrated circuits. Dr. Sato has been technical advisor of RF Domes Corporation, a startup he co-founded in 2002, dedicated to highly integrated GPS receivers. After merging with Global Incorporated, this company has been acquired by NXP Semiconductors in 2007. Presently, he is the director of scientific laboratory, jointly between Università di Pavia and ST Microelectronics, dedicated to research in microelectronics, with emphasis to millimeter wave systems for wireless communications, high-speed serial links, and read-write channel for hard disk drive.
Thank you very much. Thank you very much. Okay, thank you for hosting me in this very nice campus. I also had the chance to visit Istanbul yesterday and 2 days ago, and you don't need me to say that it's a fantastic town, but anyway, I really enjoyed it. So I could couple the two aspects, the history, visit, technical, and I also can appreciate the enthusiasm of your of the initiator of and advisor of this university. And I think it's very important that a guy at such a high level is oh no, I can. At such a high level is really close to lectures, to teaching, to research, and wants really push this reality as much as he can. So in this respect, maybe I add one aspect to the CV that was read, because in Pavia we also have inside the campus a kind of peculiar, also for Italy, and I think also for Europe, which is we host people from industry. So there is one lab that I'm presently leading, working on RFIC millimeter waves, and something also on IC for ultrasound echography, which is shared with ST Microelectronics. This means that we have 15, 20 people that are engineers of ST staying in the campus. They were former students of Pavia, and now then they were hired and back to Pavia. Together with them, we also have other PhD students, grants, so overall 40, 45 people, all involved in this area and this activity. So, oh, I knew to, okay, I prefer to stay this side. Maybe I can easily do this way. No, I think I can do it. So, okay, but it's the same. I do this way. My choice of today was, after talking a little bit with Franco, was a cut to the basics of RFIC. Basics doesn't mean that it's the same cut that I give to my master students. I will go to a faster pace. I will cover several things in depth, but starting from scratch. So the idea is touching only the receiver side, because of course I couldn't think about doing everything, receiver, transmitter, and maybe baseband in few hours. So I decided to stay on the receiver front end, giving basics in particular on CMOS IC design, which today I would say that in most commercial application is the technology used especially by industry. I would like to start from this slide that gives somehow the motivation of what we are going to study today, and in general of the evolution that RFIC has seen in the last 15, 20 years. Because if we look at a very simple FM transceiver, what we see is a transmitter, a receiver, but you immediately realize that an analog FM transceiver was done by 1, 2, 3, 4 bipolar transistors. And you can also appreciate that the operation of modulation and up conversion are done at the same time, just in this branch. And almost the same happens under reception, where you receive a signal at the antenna, and then you demodulate and downconvert to baseband. So you just need 4 devices. Usually what you learn at university, and you learn even more at industry, is that you should do the simplest thing you can. So this course starts in the opposite way, because we start from a very simple FM transceiver, and then I tell you, okay, but the reality of today is this one, which is much more complicated. So you see just building blocks. Why? Because if we should count the number of devices, transistors inside each block, we would conclude that in a chip done with this 1, 2, 3, 4, 5, 6 building blocks, we have today more than 1 billion transistors. So the question is, why did we go from 4 transistors to billion of transistors, while every course tells you should be as simple as you can? So this looks the opposite direction. And even a second aspect is that the FM transceiver, and so FM radio, and maybe also TV, are there since almost 1 century. Let's say that soon after Marconi's discovery of EM waves from Europe to US, but that was at the beginning of the 20th century. It was 1901. So why did it take almost 1 century to go to personal communication, and why were we limited to broadcasting, FM and TV? Basically because, actually the ether is known as being hostile to personal communication. And the reason is that if you think about, when you have to broadcast an information, then you have 1 transmitter and several receivers in a star configuration. So there's no confliction. There's 1 signal which is being broadcasted everywhere. Well, while when you think about communicating between several different users, then immediately you realize there will be a conflict between several users going to the same medium, and at the same time disturbing with each other, because everyone is going to halt the other one, so there is a kind of conflict between the different hosts. So the point is that just the discovery of, or the possibility of communicating over long distances through EM was not enough to enable mobile or personal communication because of this reason. Basically because it's tough to have several different users going into the same medium, which is the ether. Why is it tough? Because basically, think about in this way. For example, let's consider a communication in a urban area where you have buildings. What's happening to the EM going from one user to the base station and back? Basically is, well, you can have an array which is going line of sight to the base station, but then you can have several others that are going through reflection from the buildings. So you go through the phenomenon which is known as multipath, which at the very end, on random basis, can even happen in a signal which disappears at the base station at the receiver. So the point is, how can I guarantee a communication in such a hostile condition? And even more, how can I think about millions or let's say thousands of people in the same area communicating at the same time? So the point is that we needed to wait several other let's say discovery to really enable a personal communication. I would say that the most important one was the invention of transistor, basically because, which was in the 50s. That's basically because this allowed VLSI circuits, and with VLSI circuits you could easily go to a digital signal processing, which is much more, which lends itself much more to a good signal-to-noise ratio, good sensitivity in a hostile condition such as a communication through the ether. So this is the first possibility, giving rise to these monster that are the digital baseband processor of today that can actually improve the quality in an incredible way. A second aspect is all the information theory, which has the Shannon theorem as the major, the most important and well-known equation regulating the communication in a noisy environment. Third, probably the conception of the cellular system, so that you could reuse frequencies soon after you change an area. So you can have many different people communicating, still using the same frequencies, just moving at some distance. So this, I would say, these three aspects are those that really enabled personal communication. By the way, what's interesting to observe is that all these three discoveries were done at Bell Labs in New Jersey. And what's also interesting, and maybe this can be a discussion for lunch or dinner, is that Bell Labs now does not exist anymore. So it looks like that places where, I mean, you could do basic. I was also listening last night when in Istanbul, they were talking about Philips, and they were, in Eindhoven, where the big palace and building where they made many discoveries, especially for IC for health of today, were done, and the mayor didn't want to destroy the building because that was where they were doing these experiments. So they are renewing it, and I don't know what they are going to do, but some school or some university still to have a memory. But at the same time, what we see is that where we could do basics, science in the 20th or at the end of the 20th century looked like to have a tough mission because of economics, because everything went private, everything became a company. So, this is another aspect which makes microelectronics, I think, a little bit tough. Anyway, microelectronics and maybe more in general. Anyway, so I would say that this just as a motivation, an introduction. Why do we start from a very simple FM transceiver and we go to such complicated, transceiver? Again, I point out that here, if you add up you count all the transistors involved, you arrive at today at 1 billion easily. And even more, just to understand how each of each block or the underlying several blocks that you can identify inside require many lectures and many pages of books. Probably if you think about a book on RFIC, nowadays if it's very complete, it's in the range of 700, 800 pages. If we go to digital baseband and analog A to D, D to A converter, probably we add up another 700. So a kind of 2,000 of pages to understand everything of all these blocks. So in these 5 hours we can do much less, but still I'll try to start from scratch and go with you one by one. So especially at the very beginning, growing up an RFIC designer was not an immediate job for a teacher or for a school, basically because RF design is a multidisciplinary field, because if you consider the many aspects that an RF design needs to know, you go from communication theory, as we said just before, microwave theory about propagation of signal, here, multiple access. This looks a strange word, but means that several users need to access the medium at the same time. So the question is, how can I make them coexisting at the same time? And I said before, this is probably one of the biggest challenges that delayed a lot the advent of mobile communication or personal communication. And even more, this is probably one of the aspects for which we will see later on, we need a linear receiver. Basically because the problem is do not having interfere between the different users, so you need a linear a linear amplifier, and you need to drive this multiple access in a aware way. Then wireless standards. Of course, we need to know, we need to read the standards that telecommunication board identify, need to understand what this standard mean in terms of IC design. So this is another kind of aspect. Usually in companies, this work going from standards to IC is done by people that are known as system engineers. So it's a kind of specific aspect. Then, of course, CAD tools to make designs, then general IC design, and then knowing about transceiver architecture. This is another thing that I will cover this morning, because I think it's interesting. So you have several ways to process the signal and translate it from the antenna to baseband. So what is the best one, is there a best one, or what choice should you do, and based on what? And finally, random signals, because the second aspect that we need is being able to process a signal when it is at very low level. So what is the ultimate limit? The noise, basically. So we need to know about random signal, which in other words is noise. Because of course, the lower the noise, the better the sensitivity, and the longer the distance that I can cover with a given base station, which means that I need less base station, or I can use base station with a lower power. So whatever you want to look at it, it's an advantage. So we need to go to the extreme minimum, which is ultimately limited by random signals or noise. Works that have been published, 4, 5, 6, 7, 8, 9, 10, and you see here that now in CMOS, we can, I wouldn't say easily, but anyway, there are demonstrations of oscillators that run beyond the 300 gigahertz. So you know that millimeter wave IC design is a reality today. I'm also involved in my research team in millimeter wave stuff. You will have a lecture, I think tomorrow or in 2 days, on this specific topic. But that's very interesting if you know that we have this linear, logarithmic linear increase of both Ft and Fmax. And at the same time, you see a lot of research has been done in this year. Again, almost in the same years. You see here papers that have been published at ISSCC, which I would say is probably the premier forum for solid-state circuits, and those have the topic of RF. So you see the big increase that has been observed at ISSCC in RF papers. So this means that activity from industry, universities really contribute to move on in the field. So let's start from the very basic concepts. And I would say that, so this is really from scratch. I would like to focus on nonlinearities, in particular on intermodulation aspects, and then go to noise so that we will be able to handle the two parameters that I think need to be well known since the beginning. Again, intermodulation and noise. I said the first one because of several different uses that can coexist in the same medium. The second, to be able to understand the minimum signal that a receiver can handle with a reasonable bit signal-to-noise ratio, which in a digital environment means with a reasonable bit error rate, given the modulation of the signal. So let's start from time variance and time invariance versus nonlinearities, because sometimes this concept is misinterpreted. So even in very first books. So what do we intend, or books for first exams? What do we intend for linearity? Well, with a linear system, we intend a system where the output can be expressed as the linear combination of the several different inputs. So let's assume we have x1 that produces y1 and x2 that produces y2. Then if we multiply x1 by a and x2 by by B, then if it's a linear system, we expect to have A y1 plus B y2. So this is the definition of linearity. What is, on the other hand, the definition of time invariance? The definition is that if we have a signal at the input of a circuit x as a function of time, and this reflects into y as a function of time at the output, then if we delay the input, we expect to have a delayed version of the output for every delay. So this is the definition of time invariance. Now, you know why I do point out on this aspect? Because usually books tend to define linear circuits that are linear and time invariant, and sometimes they do not say that that definition applies to linear and time invariant systems. What do I mean? For example, that sometimes you read that when you when you have an input to a circuit, which is, for example, a sinusoid at frequency f1, then a linear system produces a sinusoid at the same frequency, maybe or generally with a different phase and a different amplitude, which is true if the circuit is also time invariant. Because if it's time variant, then it's not true, because even if it's a linear circuit, you can have at the output frequencies that can be different from the frequency that you injected at the input. This is important. I'm not doing just for teaching, but I do it because it's very important in the framework, for example, of mixers. So 99% of the mixer that you have in products or in integrated circuits are linear circuits, but still can produce a signal at the output which has a frequency different from the frequency that you injected the input. So if one thinks about the definition of a linear and time invariant circuit, can be surprised and say, how can it be? It can be possible because actually mixer is a linear circuit and time variant. So you can still produce new frequencies even different from the frequencies that you injected at the input. Okay, so otherwise one should conclude that in order to translate a signal from RF to baseband needs a nonlinear circuit, which is not true. And we would go through other problems such as interference or intermodulation that we will cover now in the proceeding of this morning. So here is an example. Let's consider the circuit on the left. We have two input, input 1 and input 2, and then we have a switch and a resistor where and we sense the voltage drop over this resistor as the output signal. So we have two inputs and only one output. So depending on which input we consider the input of the circuit, we have two different classifications. For example, if we consider the first circuit, B here, we consider the input as V in 2, what we can say is that actually this circuit will be proportional to the input amplitude of Vi in 2, and the only action that the other signal is doing is switching, opening or closing the switch. So when the switch is on, because it's habilitated by V in 1, V in 2 is going at the output. And if we change the amplitude of V in 2, changes also the output amplitude. So the signal gives a proportionality between input and output, and in this sense is linear. Of course, it's not time invariant, because depends not only on the timing of the input signal, but also on the timing of the second signal that regulates the switch. So this will be time variant. Let's look at the same circuit under a different view, which is we consider V in 1 the actual input and V in 2 a secondary input, and we detect the output at here again. Now, of course, in this case, the output will not be time invariant and will not be linear. Why? Because basically, depending on the fact that V in 1 is habilitating the switch, for example, being positive, we will have an output which is equal to V in 2. And on the other hand, if the signal, the switch is off because the signal is negative, then we have 0 at the output. So what means is that we are insensitive to the amplitude of a V in 1 because V in 1 is just needed to switch, to open or close the switch. So in this sense, this circuit is nonlinear and time variant. On the other hand, the one on the top is linear but time variant. So how can we look at this circuit in the time domain? So if we write down V in 1 as a cosine, A1 cosine of omega 1t, and the second signal V in 2 as A2 cosine of omega 2t, and you see here the two plots, V in 1 and V in 2. So what's happening at the output is that if we consider the switch closed when V in 1 is positive and open when V in 1 is negative, then the result is this time domain plot where you see V out is identical to V in 2 when V in 1 is positive, and then is 0 when V in 1 is negative, and again when V in 1 is positive. So we have a kind of modulation of the signal injected in V in 2, and we can look at it as a multiplication between this sinusoid times a square wave that toggles between 1 and 0. So when the switch is off, we have 0. When the switch is on, we have 1, and we repeat V in 2. So we can look at this system in an equivalent way as if it were solicited by an input sinusoid multiplied by a square wave which toggles between 0 and 1. Okay? Still, again, it's a linear circuit. I repeat it because maybe it's not immediate, but it's a linear circuit because if we change with respect to V in 2, because if this amplitude increases, then also when different from 0, also the output will resemble the IN2 input. So it's proportional and it's linear. And still we can view it as the product of V in 2 times a square wave toggling between 0 and 1. Okay, so if we look in this way, we can simply transform or look at in the frequency domain, or better, we can think about the spectrum of V in 2 convolved times the Fourier transform of a square wave, which is given by this expression, where you have a series of delta function. Now, if you solve the convolution of this expression, you arrive at this final form, which tells you that starting from a signal which has power at a frequency f, you move to an output signal where the power has been translated by a factor which is n over t1, where t1 is the period of the switch. Okay? So the point is that if the circuit is time variant, then you see, still it's linear, you see that we can produce new tones even if at the input we had different one. So it's linear, but time variant, and you see that, of course, depending on the frequency, in this case of the switch or the signal that drives the switch, we can produce new tones. Okay? So we didn't need a non-linear circuit to do it. Is this clear? Because I understand this can be a little bit tricky. So if this is clear, or if there are questions, please do, because this is an important task, very important in my opinion, because otherwise one can think about for a mixer that we will, because once this is clear, we can immediately understand that there's a way so that I can have an input signal at some frequency and generate an output which is at another frequency, still with a linear circuit. So this is what I would like to do when I receive a signal at the antenna and move it at some point at baseband. I want to do it, but if I can do it in a linear way, as we will see later on, that's the best I can do. Because, of course, there are ways to do it also in a nonlinear way, with nonlinear circuits, but those are less effective and let's say, other problems can come along. So this is one, I would say, of the most important aspect to be focused at the very beginning, at least before moving to mixers and to down-converting blocks. So why do we need to be very careful and do not misinterpret time variance for nonlinearity? Basically, this is an example, and let's see what's the effect of nonlinearities in a circuit. So let's start from, there are several aspects I would like to cover. Let's start from harmonic components. So let's assume we have a system that can be described by a polynomial, so that the output is a polynomial of the input x of t with the coefficients a1, a2, a3. So let's assume we have an input which is a very simple sinusoid, a cosine of omega 0 t. So what is the output? So we introduce this cosine in this expression. So this is what is done in the first row. And then we start with some reminding of high school Prostaferesi equations. We start manipulating them, and the result is that we have a first term, which is exactly the linear term. Then we have second order components that we can write in this way as a DC component plus a second harmonic. And then we have third order components that you see here, a3, a to the cube over 4, and then 3 times omega 0 plus cosine of 3 omega 0 t. So if we group now the different components, we have a DC, a linear term, a second order term, and a third order term. So first thing, and this is as a comment, first thing to comment is that you can see that basically higher order terms, such as the second and the third, are generated only in the presence of second order coefficient or third order coefficient respectively. So this means that if a circuit doesn't have for example, nonlinearity of second order in its nonlinear relation, then I don't have any second harmonic. Okay? This is important, and we will see it in the framework, for example, of direct conversion receivers, where we care about second harmonic, and means, if you are an IC designer, that, for example, if we are using a fully differential gain stage, which doesn't have any second order term, then we expect not to have any second order problem. So in some sense, in a direct conversion architecture or in a framework where we need to go and we care about baseband components and second order components, we should go for a fully balanced circuits. Now, actually, we will still suffer from second order components, even in a fully differential structure in the framework of a direct conversion, but only because any circuit is at the very end asymmetric. You should think about offset. Two transistors are only nominally identical. Once you make 1 million nominally identical transistors, you discover they are different. And you have, of course, a statistic of difference. So this statistics makes any circuit asymmetric. So whatever you are doing, even a fully differential circuit, you will end up with an A2 components that will give rise to second harmonics and second order intermodulation in direct conversion. But in principle, this is the way to go because it's only a second order effect. While if you do not select a circuit in such a way, you do not have a second order coefficient, then you will, of course, suffer a lot of these kind of problems. Okay? Okay, another thing which is very interesting, and I think probably not so easy to predict, is that also the linear coefficient is not only determined by the linear coefficient A1, but here we also have a contribution from the third order component, so the coefficient of the third order nonlinearity of the input-output characteristic. So what does it mean? That the coefficient of the linear component is going to change if the amplitude of the signal increases. So at the beginning, we have in a linear, in a properly in an actual linear circuit where the signal is small, then we expect to have a gain which is A1, and the amplitude, this is just A, the input amplitude, so the gain is A1, and we expect to have it constant, at least in the linear regime where the signal is small. But once the signal increases, we expect to have, given this nonlinear relation, a polynomial, to have another contribution which changes the picture. So is this a problem? Yes, this can be a problem because let's assume that, for example, the coefficient A1 and A3 have opposite sign. So A1 times A3 is a negative number. What does it mean? This means that I'm, for example, increasing the output in a linear way, but at some point I have a subtraction, which is more and more important when A increases. So what I can expect is that I have a linear behavior, but at some point this increase bends, and I tend to have a saturation. And keep in mind, we'll see later, looks like we will see everything later. I hope we will have time. Anyway, we will see later that this is actually happening, for example, in a fully differential amplifier. So the two coefficients have opposite sign. So what we expect is a compressing behavior. Compressing means that we have a linear behavior followed by a saturation. So in most of the circuits, especially if we use a fully differential approach, we expect to have a compressing behavior, which means that at some point, once the gain is large enough, the output tends to compress. So we deviate from the linear gain, and ultimately, when this curve becomes parallel to the x-axis, the gain drops to 0. So the circuit doesn't have any gain. Okay? So we define a parameter which is the 1 dB compression point, which tells how much tells us what is the input amplitude for which the output is deviating from the theoretical linear behavior by 1 dB. Okay? So again, if we didn't suffer, we had an ideal linear circuit, we would expect this line to go straight indefinitely to infinite. Because of this third order component, we start compression. So we define 1 dB compression point as the output amplitude for which the gain has dropped by 1 dB with respect to the ideal linear straight line. Okay? So we can go to some quantitative result, and write this in equation what I explained now. So we can say that in a log scale, 20 log, or in dB, 20 log A1 plus 3A3 A squared over 4 is equal to 20 log A1 minus 1 dB. So when this quantity has fallen by 1 dB with respect to the linear gain, A1, then we have the 1 dB compression point. So solving this equation, we arrive at this expression. A1 dB is equal to the square root of 0.145 A1 over A3. This is useful, and we will relate it to some other parameters. Now, actually, the question is, being expert of IC design and communication, is compression really a problem from your intuition in a circuit for mobile communication, wireless communication, in the framework of our interest of today? Do you think that this phenomenon that I described right now is always a problem, is never a problem, is sometimes a problem? Do you have any intuition about it? Yeah. He's completely right. And in fact, let's, for example, think about a signal that carries information in the amplitude. Then in that case, we are changing the information because of the compression of the circuit. It's a little bit less problem when we are carrying information in frequency or phase, because in that case, maybe we have limited the amplitude. So even if we're compressing that amplitude, it's less problematic. On the other hand, it's completely true that almost every, especially modern communication modulation, has some amplitude variation for many reasons. So usually the amplitude varies, and we need to be careful about compression. We do have one countermeasure for compression that we do not have if we move to the so-called desensitization. Because for desensitization, we'll see right now, we intend almost the same phenomenon, but related to an interferer, which is not the signal of my interest. Now, once I've been talking about compression, I've focused the signal that I intended to be the input of my circuit, so the signal that I want to detect. Now, if it's the signal I want to detect, and I restrict the problem to that signal, then there is one more thing I can do. Because if I see the signal is strong, then I probably do not have a problem of signal-to-noise ratio, because it's a strong signal. So I can think about changing and reducing the gain of the receiver. So I can reduce the gain and attenuate a little bit the problem of compression. But if the problem is not coming from my signal, but from an interferer, so I'm in a situation where I'm thinking about two tones. One is my tone, maybe a weak tone that I'm reading at sensitivity, plus a signal which is a big, strong interferer. So if this is the situation, still the phenomenon is the same, because the strong interferer is at a different frequency, but let's assume it's slightly different, so that still falls in the band of the linear amplification. So in this condition, what happens is that there's nothing I can do, because this is an interferer and I'm receiving the weak signal. So I cannot reduce the gain, because if I reduce the gain, my weak signal is seeing a signal-to-noise ratio which reduces. So I need to make them coexisting. So this is why I really need to have a circuit which is as linear as I can, because otherwise I will suffer from compression. And in particular, let's see these equations. Let's assume we have these two tones. One, for example, is our weak received signal. The second is the interferer. We still develop the mathematics, And we arrive at this expression, which is identical to the one of before. But now we have A2, which is an interferer, and A1 is my received signal. So now for large A2, the gain can eventually drop to 0, and I have no gain, and this is a condition which is known as desensitization. And you say that the block is desensitized, which means that you are not gaining anything, and basically you do not receive and detect anything. So this is why a block in the linear front end of a wireless receiver need to be linear. Of course, linear as much as you can. At some point, you will have an A3 coefficient, because there's nothing which is linear, indefinitely linear for any input amplitude, because basically transistors are nonlinear. What time is it? Okay. Okay, is there any question here? Is it rather clear? Okay, so one aspect of still related to nonlinearities is the so-called, second one, is the so-called cross-modulation. This happens when the interferer is also amplitude modulated. If we have an amplitude modulation to an interferer, then what's happening is that the modulation is transferred to the signal of interest. In this case, we can assume a weak signal of interest. And still, this is due to nonlinearities. If you look at the former expression, and you introduce a signal which is amplitude modulated, so A2 times 1 plus m cosine of omega mt, which is the amplitude modulation, times a carrier. Okay, so if we introduce this signal inside the nonlinear expression of before, we end up with this final expression. We have the linear coefficient plus, proportional to A1, plus another contribution where you see the dependence from the modulation, M. And basically, you also see, so you see that starting from this condition, where we have omega 1, the signal of interest, and omega 2, the modulated signal, we assume at the input at two different frequencies, because of nonlinearities, you see that cosine of omega 1 has a modulation which was carried by omega 2. So you see that at the output, you at least expect the same modulated signal, the linear signal, but also a residue of amplitude modulation, and this is produced by nonlinear component. For example, this is a big problem in TV tuners. For digital TV, in TV tuners, you have big channels with amplitude modulation, and you cover a frequency range which goes up to 1 gigahertz and spans from less than 100 megahertz. And what is happening is, if you are not careful, you encompass the problem of cross modulation because of nonlinearities. Another aspect which is very, very important, I would say, together with the sensitization, is the other nightmare of a linear front end for wireless application, is third order intermodulation. And it is still another aspect of nonlinearities. So let's again think about the same nonlinear equation, 1, 2, 3 coefficients, square cube, and let's assume again to have two tones, not only one tone. Now, we considered one tone to identify the harmonics. Then we still considered one tone to talk about gain compression. Then I said, let's move to two tones. One is our received signal, one the interferer, and still we analyzed the sensitization. Now, let's go to two tones and then we will try to interpret what these two tones can be. Let's look at the mathematics, and then let's try to understand what can produce the problem that I'm going to talk about now. So the two tones are generically expressed by A1 cosine of omega 1 t plus A2 cosine of omega 2 t. So there are, if you introduce this expression inside, what you find is that there are several intermodulation products where intermodulation means that are produced by squaring and elevating to the cube this addition of two tones. So instead of writing down all the components, which can be a little bit boring, I do limit and ask you to trust me that this is a result. So if you, for example, elevate to the cube the two tones, you can intuitively understand that at some point you will have one tone squared times the linear component of the other one. If you do that, at some point you also, due to prostapherisis, you also expect to have something which is of the kind 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Okay? Is it clear? Okay. So let's focus the attention to these two, produced by 2 omega 1 plus minus omega 2 and 2 omega 2 plus minus omega 1. We have these two and these two. So let's focus the attention in particular to 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Why do I focus these two components and tell that those are particularly important? Because basically, if we think about a typical telecommunication application, we have several users, and typically we have one user after the other, and they are apart for a fixed frequency span or frequency difference. So we have one user at f1, another one at f1 plus 1 megahertz, for example, another one f1 plus 2 megahertz. So they are spaced in a rigorous way, one after the other. So if we have two tones at omega 1 and omega 2, for example, let's assume omega 1 is 900 megahertz and omega 2 is 900 megahertz plus 1 megahertz. Where is falling 2 omega 1 minus omega 2 or 2 omega 2 minus omega 1? So, for example, 901 megahertz is omega 1, 2 times is 1802 megahertz, minus 900 megahertz means 900 megahertz and plus 2 megahertz. So, this contribution due to third order nonlinearities is falling to the alternate channel. So we have 900, 900 plus 1, those are interfering, and they produce an interfering product which is going to the alternate channel, which is 1 megahertz apart. The same thing happens if we think at the intermodulation of 2 omega 2 minus omega 1. 2 omega 2 now is 901, so, sorry, 900. 900 times 2, 1800, minus 901 means 1899 megahertz. Okay, so we start from two tones, they intermodulate and produce products that fall aside, but they go into channels that are occupied by alternate users. So due to third order intermodulation, the picture is this one. We have at the antenna, our signal, which is again, for example, at GSM at 900 megahertz. Actually, it's not exactly 900. I was thinking about the exact GSM. So, yeah, exactly. 25, I think, the first. Yeah, let's say. Anyway, let's do it with the 900. 900, 901, and 902. So let's assume those are just two other channels, and this is the received one. So due to intermodulation of these two, we still have at the output the input signal, the two interferer, but then we have intermodulation of the two, which is falling inside the signal of interest. Of course, this power inside this frequency band cannot be recognized and made distinct from the power of the signal itself. So this is going to limit the signal-to-noise ratio. Okay? Okay, so let's make some more calculation, which will be also interesting and useful for easy calculation when you are doing some design or you are making measurements. So we have the two tones, and we introduce in the usual nonlinear expression of before, and we arrive at these several components. We are interested in these two, 1 and 2. So we can define AIP3 as the input amplitude for which the third order components, so the coefficient of these two components, this one and this one, are equal to the linear component, so this one. So let's assume, as is typically the case, that A1 is much larger than this quantity, at least where IIP3 is of concern, and we have A1 IP3 equal to 3 over 4 A3 A cube AP3. So this defines this quantity, which is the input amplitude for which linear component and third order intermodulation are equal. So the expression is AP3 is equal to 4 over 3 A1 over A3 square root. So what we said is that we have a linear component, omega 1, omega 2. We generate third order intermodulation components due to nonlinearities. The coefficient were 3 over 4 A cube. So we can write at the output A omega 1, the linear component, is A1 times the input amplitude. Then third order intermodulation amplitude, 3 A3 A cube over 4, which gives an expression of 4 over 3 A1 over A3, 1 over the amplitude square. So this means, if we think about, if you look again at the former slide that gives the expression of IP3, 4 over 3 A1 over A3, that here A omega 1 over A IM3 is equal to A square IP3 over A square of the input. This is interesting. Why? Because it lets you make an immediate calculation from one simulation in principle or one measurement in principle. Why? Because basically here we relate the linear output amplitude, the linear product, the third order intermodulation product, to IP3 and the actual input amplitude. So looked at in another way, we can write it in log scale and say that 20 log A omega 1 minus 20 log A IM3 is equal to 20 log A square IP3 minus 20 log A square in, which means that AIP3, the amplitude for which, again, we have input linear components equal to third order components, is given by 1/2 20 log A omega 1, so the output amplitude, linear amplitude in dB, minus third order intermodulation component in dB, plus the input in dB. So if we call this quantity delta P, the difference of power, we can immediately say, let's do a measurement or a simulation. We introduce an amplitude at the input AIN1, and we measure the linear component at the output, A1. We measure the third order intermodulation, AIM, and this is delta P. So if we divide delta P by 2, look at it here, by 2, and add the input amplitude in dB, so the input amplitude in dB, plus delta P over 2, we have IIP3. Okay, so this is a very simple expression that for very easy and fast determination under measurements or simulation, you just need to introduce an amplitude A, measure or simulate the linear and third order components, and you immediately have this parameter, which is probably the most important parameter to identify intermodulation, for example, in mixers or in linear circuits where linearity is critical. So again, the expression is looked at with frequencies, omega 1, omega 2. We generate the third order intermodulation. We just need to measure this difference at the output, delta P, and then we have this expression of IIP3. Of course, don't do it, or at least make some verification, because this assumes that everything is correct. So especially under measurements, this can be a little bit scary, because it's true that this is the way to go, but we assume that this is exactly a third order straight line. This is exactly a linear component, whereas you need to verify under simulation or measurements that actually you are having detecting a third order nonlinear problem, and you are not suffering, for example, for fifth order, seventh order, or other nonlinear components that would change this line and would tell you are in the wrong direction because it's not a third order intermodulation problem. So you need to actually measure many more points so that you can build this line and verify that the slope is 3 times the slope of the linear components. Okay? But for a very fast and to have an idea, especially when you have been waiting for a chip for a long time, your goal is the high IP3, and you want the students to know if the result is coming out, then one measurement can give you a lot of results. Usually, the first measurement either tells you that nothing is going or everything is too nice because you are in a hurry. But this is the best way to have an idea of high IP3. Then you need to verify that you are really measuring third order intermodulation and not something else. Okay? Is there any question? Because I mean, I'm saying many things. Yes?
Yeah, my question is, you're looking at two interfering frequencies, right? W2, W1. What if we had a third one?
Actually, you mean if you have a third one on this side, for example, 1, 2, 3?
Right. And then I would have your modulation coming from another combination, for instance, W2 plus W3 minus W1 would probably lie somewhere in your desired band as well.
Yeah, I mean, in that case, you may have also fifth order and others, but those are the...
Even in the third order.
Yeah, but I would say that those are producing the most important problems. Are you thinking about something specific with 3?
I'm thinking, let's say we have 3 components, 900, 901, 902, right? Let's combine 900 and 902.
Then you have
yeah. And subtract 901.
You know,
so you actually get,
yeah.
right on top of your signal, you get the third order intermediate.
You know what's happening? If you think about the third one, you are probably producing other 1, 2 falling aside. So if you are interested, so apart from these 3, let's say 1, 2, 3, and your is this one. So those ones still are producing something here, while those one would produce something here, which is not of your interest in this moment, because your user is here. Okay?
In multiple access, you want to demodulate everyone, right? So
Yeah, but I'm thinking now about, okay, you're meaning, for example, in base station where you need to do it. Yeah, that's another problem. But usually as a mobile user, you receive one channel. So in that...
you're thinking in terms of downlink.
Yes, sure. This is down. But also in Downing, when you are in a base station, then you need demodulate everything all at once. So. Use.
Well, this 9.6 degree is a rule of thumb by all.
Yeah,
It doesn't work all the time this way. For example, generally, students with MS workshop. But generally, with respect to manufacturers, they never, because their electricity should be about 9 decibels. You can easily observe that.
You're right.
Sometimes 12, 15 less. So
Yeah, you're right.
I think you're right, because you get you to the fact that you cannot measure. You cannot
Yeah,
measure
he's perfectly right.
what you can measure
True.
quality compression.
Yeah.
Measurable point, but that one is calculable point.
That's true. So he's perfectly right. As I said, this is, let's say, to introduce the different aspects. I'm going from scratch. So this is more a mathematical result than that in many cases cannot be applied. It's correct, but cannot be applied. Why? Basically, because what we have behind this result is that we expect to have only third-order intermodulation, and we all, what's your name? As Olun is saying, the point is that IIP3 cannot measure as a value. So you'll never be able to measure the IIP3 of a linear circuit directly because this is an extrapolation. Usually, if you consider what is the IIP3, we'll make some examples, but what is the IIP3 of a circuit, then you would easily end up with something in the order of 20, 30 volts for a supply of 1 volt. That's because it's an extrapolation. It's just the value that would produce a nonlinear third-order component equal to the linear component. You can understand that this is an extrapolation by the fact that if you really could be able to have an IIP3, well, you had IIP3 of a value lower than, for example, the voltage supply, this would mean that for that input, the signal to a third-order intermodulation ratio would be 1, which just because of 1 or 0 dB, you would never be able to measure anything because the signal-to-noise ratio can be in the order of 7, 8 dB, all included, noise, intermodulation, phase noise, whatever you have. So, of course, if this were a measurable value, would mean signal-to-noise ratio of 1, which wouldn't be. So the IIP3 is in excess, much larger than the voltage supply. And so even this is basically one of the major reasons. So usually the 1 dB, which is a measurable value, is of course lower than the supply. So this value is, especially with a good mixer or good linear circuits, is not respected because you can have much more than this difference. But theoretically, this is just a cross-check. You cannot have lower than this. So this is just, okay, given the assumption is correct. But in many practical circuits, this can eventually not be true. Okay, so one example to determine nonlinear coefficients of a fully differential circuit, usual polynomial, a1x1, a2x squared, a3x cubed. So a1 will be the derivative of the output versus x for x equal to 0, a2 1/2 of d squared over x 2 times, and so on. So let's write ID1 minus ID2, the difference of the two drain currents, as a function of the input voltage. So just assuming devices with the square law, we arrive at this expansion, which tells that ID1 minus ID2 has this possible series expansion, considering this term much lower than 1. And what we end up with, I don't make all the calculation, but what we end up with is that A1 is given by this expression, and A3 is given by this expression. First thing to notice that I said at the beginning is A1 has a sign which is different from A3, which justifies the compression nature of most circuits that you encounter. And this is just a very simple differential pair. And second, this is the expression of IIP3 using the formula found before, and we can express it versus the overdrive voltage, which is usually the most important parameter of quoted for circuit comparison or for circuit description. So IIP3 of this simple, fully differential pair is given by the square root of 6 times the overdrive. So this is interesting because you can see here, and maybe a little bit surprising. So I want to see who can have an intuition about it. So I said we assume square law M1 and M2. Okay, so this current is related to VGS by a square law relation. The same for M1. And at the very end, we end up to a third order component, A3, which gives rise to this expression. But how can it be possible? Because we start from a square law, so we do not introduce a third order coefficient, but still the final ID1 minus ID2 versus Vin has a third order coefficient and is responsible for third order intermodulation. So is there some intuition about it?